Good afternoon. This is Professor Shannon Gracie. We'll be working on the graph of a rational function during this little class. And we are working from Sullivan and Sullivan's Precalculus Enhanced with Graphing Utilities text. So let's go ahead and warm it up by finding the zeros of this rational function. So to find the zeros of the rational function, you want to think about it in the easiest way possible. So when you have a fraction, if 0 is in the numerator, then the whole fraction will zero out, unless you also have a 0 in the denominator. But you can worry about that when you're in calculus. So here we go. Let's go ahead and warm up. So if I set r at x equal to 0, I will find the zeros of the rational function, which will also be the x-intercepts. So let's go ahead and I think I'll use the quadratic equation here, or quadratic formula. So x will be equal to the opposite of 3 plus or minus the square root of 3 squared minus 4 times 5 times negative 4 all over 2 times 5. So we'll have negative 3 plus or minus the square root of 9 plus 80 all over 10. So we will have x is negative 3 plus or minus the square root of 89 divided by 10. So we have two situations. X can be equal to negative 3 minus root 89 all over 10, or x could be negative 3 plus root 89 over 10. So getting the approximate results, we will have clear this stuff out. Okay, so I'm going to put parentheses and we'll have negative 3 minus the square root of 89 divided by 10. And so we get approximately, I think it said to the nearest tenth, so approximately negative 1.2. And then over here, x would be approximately, so I'm going to hit second enter and then just change the minus to a sum, and we get approximately 0.6. So negative 1.2 and positive 0.6 are the approximate real zeros and the x-intercepts of this rational function. All right, now that you're all warmed up, let's just summarize how we analyze the graph of a rational function. So it's always good to factor the numerator and denominator of r, and then find the domain of the rational function. Write r in lowest terms. Locate the intercepts of the graph. The x-intercepts, if there are any, satisfy the equation p at x is equal to 0, as we talked about in the warm-up problem. The y-intercept, if there is one, will be r evaluated at x equal to 0. Now, what you want to do is locate the vertical asymptotes of the function. The vertical asymptotes, if there are any, when you look at R at X in lowest terms, are found by identifying the real zeros of the denominator Q at X. So each real zero of the denominator gives rise to a vertical asymptote. Whoops, denominator. Alrighty, and then we will be locating the horizontal or oblique asymptote using the skills you learned from the last section. And then we want to determine points, if there are any, at which the graph of R intersects this asymptote. So just check section 4.4 if you forgot how to do this. Then, like we said before, in Precalculus, we still have to use our graphing calculator to complete the graph of the function, or at least check our work. And then we'll use the information we found to sketch the graph by hand. All right, so factor and identify the domain of R. So here we go. The denominator, what I mean by factor on this instruction is factoring out the denominator. So the denominator is already simplified. So we want to figure out when it's 0, because any x values that yield a 0 denominator must be excluded. So the domain of R will be, in set notation, x such that x is not equal to 1, and in interval notation, minus infinity to 1 union 1 to infinity. So we're excluding 1 by having parentheses around it. Next up, write R in lowest terms. So R, it's fairly uncomplicated, but let's see, R of x was 2x plus 4 divided by x minus 1. So we could factor out a 2 from the numerator. So to find the x-intercepts, you set the numerator equal to 0 and solve. So if I divide both of these by 2, the 2 divides out on the right side, and we get a result of 0 on the left. So 0 is x plus 2, and negative 2 is x. So at x equal to negative 2, there's an intercept, or you could write the ordered pair, negative 2, 0. Okay, the y-intercept is found by evaluating R at 0. So remember that it was 2 times x plus 2, so we'll have 0 plus 2, over 0 minus 1. So R at 0 will be equal to 4 over negative 1, which is negative 4. So we get the y-intercept at y equals negative 4, or the ordered pair 0, negative 4. And the better you are at doing these by hand, the easier curve sketching and calculus is going to be for you. Okay, so now let's locate the vertical asymptote. So now we already had worked with this. We would set the denominator equal to 0 and solve. So in this case, we're not saying does not equal, because we're looking for the line that is the vertical line that represents the vertical asymptote. So that'll be at x equals 1. horizontal or oblique asymptotes. So if you take a look, we'll just look at r at x in the original form, which was 2x plus 4 divided by x minus 1. So they have the same degree, so we need to divide. So my divisor is x minus 1, and then I've got 2x plus 4. So if I multiply by 2, I believe that will do it. So 2x minus 2. Don't forget to distribute the 2 through the x minus 1 quantity. And we will get a result. Minus a minus 2 is plus 2, so we'll get a result of 6. So basically, we found out that r of x can be rewritten as 2 plus 6 divided by quantity x minus 1. So y equals 2 is the horizontal asymptote. How's it going so far? You can do it. Just hang in there. It all will start to make sense, I promise. Okay, so then it says use a graphing calculator to graph the function. Just for fun, what I want to do is I want to use the information that we found and make a sketch of the graph. And I want to see how, how we did. And then we'll match it up. So this is r of x, and this is x. All right, so we had, if you recall, a vertical asymptote at x equal to 1. So the graph won't cross this line. And then we had a horizontal asymptote at y equals 2. We could cross this line potentially. So we'll have to be careful to check for values. So we also have a couple of ordered pairs already. Our x-intercept was at -2, 0. And our y-intercept was at 0, 1, 2, 3, 0, -4. So let's get a few more ordered pairs, right? So I think we have a pretty good feel for what's going to happen on that bottom left part of the graph. But just to make sure, why don't we figure out, so let me rewrite r of x was 2 times x plus 2 over x minus 1. So r evaluated at, let's do negative, I don't know, how about -5 will be 2 times -5 plus 2 over -5 minus 1. So that will be -5 plus 2 is -3. So we'll get -6 over -6, which is -1. Is that right? Let me just double check that one. So let's see, 2 times, that is -3. Oh, my bad. This will be +1. Sorry, this is movie 3 for today, so getting a little crazy. All right, so here we are. So do you see that this is likely going to follow this pattern? That would be my educated guess. So now let's see what's happening on the other side. Actually, I don't like this part of it. Okay. So now let's check out the other side. So if we evaluate r at 2, we'll get 2 times 2 plus 2 over 2 minus 1. So that's going to be 4 times 2 is 8 over 1, so we'll get 8. We get an ordered pair here. And then r at, how about r at 5? We'll have 2 times 5 plus 2 over 5 minus 1. So that'll be 7 times 2 is 14 over 4, which is 7 halves. So 7 halves is 3.5. And we have something like this. So do you see it seems to be trending in the same way? I'm going to go ahead and find out what r at 3 is, just so I can get that middle value. And then we'll move on. So 3 plus 2 is 5 times 2 is 10 over 2, which is 5. So it's going to look, I believe our graph will look like this. So let's see how close we came. So if we go to our graphing calculator, we have so our original graph was 2x plus 4 divided by, and you need to make sure the numerator and denominator are each in parentheses, x minus 1. And this is a little bit different scale, so let's go to, let's try zoom square. And actually first we'll go to zoom standard. And then we'll go to zoom square, because that way it'll go more like our graph. And look, it looks pretty similar to what we got. We'll go ahead and paste it up here so you can admire your work. And then you can say, yay, we did it. Or we'll say it matches. Okay, so we just basically have a couple more problems just like this. So here we go. With this one, and again, if you feel confident about this, please pause the movie and we'll go ahead and I'm going to copy this so that we can always see the original. But feel free to, pause the movie and work these out yourself if you feel confident. Okay, so here we go. So let's take a look at that denominator. So x squared plus 8x plus 15 cannot be equal to 0. So factoring, this factors I think is x plus 3 times x plus 5 cannot equal 0. So x plus 3 cannot be 0, or x plus 5 can't be 0, which leads us to x not being equal to negative 3, or x not being equal to negative 5. So our domain is, in the set notation, x such that x is not equal to negative 5 and negative 3. And in interval notation, you'll have 3 intervals. So minus infinity to minus 5. union minus 5 to minus 3, union minus 3 to infinity. So there's our domain. Here we go. Now we want to write r in lowest terms. So remember that r was equal to this. We've already factored the denominator, so let's take a look at the numerator. The numerator factors as, looks like x plus 5 times x minus 2 over x plus 3 times x plus 5 from before. So the x plus 5's divide out, but don't worry, you're still good for your domain because you still would have had to exclude x as negative 5. So the simplified version here is x minus 2 over x plus 3, but we have to add in here that x cannot be equal to negative 5 since that factor has divided out. So let's find our intercept. So we'll work with the simplified version. So if I set the numerator equal to 0 and solve, I get x is equal to 2. So at x is 2, or the ordered pair, 2, 0, we'll have our x-intercept. The y-intercept we'll get by evaluating r at 0, which will be 0 plus 2 over, what was it again? Oh, 0 minus 2 over 0 plus 3, which is negative 2/3. So the y-intercept occurs at y is negative 2/3, or the ordered pair 0, negative 2/3. Okay, so locating the vertical asymptote. So it's kind of, interesting. Since that x plus 5 divided out, we will just have one vertical asymptote. So remember that r of x was x minus 2 over x plus 3, x not equal to negative 5. So x plus 3 equal to 0 gives us x equal to negative 3 is our vertical asymptote. So there, the vertical asymptote is at x equal to negative 3. And let's just write down what's happening with negative 5. There is a hole in the graph. At x equal to negative 5. So you won't get a whole line of excluded values. You'll get a single ordered pair that's excluded at x is negative 5. Okay, so locate the horizontal or oblique asymptote. So again, working with the simplified version, which was x minus 2 over x plus 3, where x is not equal to negative 5. If we divide, we'll have a 1 here, and multiplying we get x plus 3. Subtracting, we'll get, let's see, negative 2 minus 3 for that second part, so negative 5. So what we have found is that r at x can be written as 1 minus 5 over x plus 3. Again, we have to exclude negative 5. So that means we have another horizontal asymptote. So horizontal asymptote at y equals 1. All right, moving right along. We will have, again, I think we should use our graphing calculator at the end, and we'll see how we do. So here we go. We have r at x and x. And we have our vertical asymptote was at x equals -3. We had a horizontal asymptote when y was equal to 1. And then we have to be careful because remember we have to exclude that one value at x is -5. So why don't we figure out, remember that r at x in the simplified form was x plus 2 over, no, x minus 2, right, over x minus 2 over x plus 3. Make sure I did that when I was dividing. Good, I did. All right, so r at -5, we'll go ahead and evaluate it, but then we'll be putting an open circle there to show it's not included. So this is going to be what, -7 over -2, which is +7/2. So if we go to -5 and we go to 1, 2, 3.5, there's an open circle. So you got to make that an open circle. I want to make it really obvious. Okay. And then now we already have our intercept. So we had our x-intercept at 2, 0. We have our y-intercept at 0, -2/3. And then let's just find some other ordered pairs, right? So let's take a look at r at -2, just to the right of that vertical asymptote. So we'll get -2 minus 2 over -2 plus 3, which is -4 over +1, which is -4. So ordered pair at -2, -4. And so I think we have a pretty good idea of what's going to happen on that side. And then let's check out the left side to the left of that vertical asymptote. So taking a look at r at -4, we would get -4 minus 2 over -4 plus 3, which is -6 over -1, which is +6. So at -4 we'll be at 1, 2, 3, 4, 5, 6. And then r at, why don't we do r at -8? How about that? So we'll have -8 minus 2 over -8 plus 3, which is -10 over -5, which is +2. So it's going to look something like this. So you're going to, whoops. So we're going to stop right there to keep our open circle and then go up like this. All right, so let's do our graph and see how we did. So with the graphing, it's always kind of good to do your original graph to see how close you got. So let's clear this one out. And our original function was x squared plus 3x minus 10 we're going to divide that by x squared plus 8x plus 15. So let's see what it looks like. So here's one kind of interesting thing. It's a flaw of the mighty graphing calculator. If you look here, the graphing calculator doesn't seem to have excluded the one value, right? But we know it needs to be excluded. So this was our R of x, and our scale was negative 10 to 10. So basically, yay, again, it matches. But let's just take a look at the table. So at x equal to negative 5 and negative 3, you see an error. So we expected that with the negative 3 because we had our vertical asymptote. But do you see that you don't see anything on the calculator that shows you that, which really kind of sucks. So it's good that you're getting your math skills going so you're not tricked by that. So if you see right here, this is where the open circle is. And notice here, it doesn't show up on the graph. Okay? Alrighty. So one more of these, and then we have a little application, and then we'll be done for the day. So here we go. We can, it depends on how you want to look at this one. Why don't we get it as one happy rational function? So that would mean, if you worked a little with R of x, this isn't quite factoring, but do you guys see that? So we have 2x over 1 plus 9 over x. So what we need here is this guy needs to be adjusted. So r at x can be written as 2x squared plus 9 all over x. So the domain is basically going to be that x cannot be 0. So or in interval notation, so there we go. All right, so write r in lowest terms. It already is. And then let's find the x-intercepts. So if you set 0, the denominator equal to 0, and solve, we would get this, and x squared would be equal to negative 9 halves. So do you see that that's imaginary? So we won't have any x-intercepts, so we'll just write none. Okay, the y-intercept, if I evaluate r at 0, I would get 2 times 0 squared plus 9 over 0, which is 9 over 0, which is undefined, since 0 is in the denominator. So we do not have a y-intercept either. So let's locate the vertical asymptotes. So again, r at x was 2x squared plus 9 over x. So it's just at x equals 0 is our vertical asymptote. And locating horizontal or oblique asymptote. So rewriting this in the format it started out with, So we had changed it to look like this. But remember, it started out looking like this. So you don't even have to do any more. We end up getting an oblique asymptote. Oops, I switched. Oblique asymptote at y equals 2x. It's this part of it. And so there will not be a horizontal since we have an oblique. Okay, so again, we'll use our graphing calculator just to check. So let's see what we have here. So we had our vertical asymptote at x equal to 0. We have an oblique asymptote at the line y is 2x. So we'll dash in our oblique asymptote. Okay, so this is the oblique asymptote. So let's check out what we have going on. You know, I'm thinking that this one might be, so r at x equal to 2x plus 9 over x. Let's see if this is odd or even. We might get lucky. So we would get negative 2x minus 9 over x. If I factored out a negative, I'd get negative times quantity 2x plus 9 over x. And do you see that that's equal to negative r at x? So r is odd. And so that means it is symmetric. So the graph is symmetric with respect to the origin. Okay, so that'll help us. We just need to find a few ordered pairs. So let's find out what is r at, how about negative 2? So that would be 2 times negative 2 plus 9 over negative 2. So negative 4 minus 9 halves, which is negative 17 halves, or negative 8.5. So we have an okay, so let me make sure, double check my ordered pair there. So we would have, oh, I didn't go down negative, that's what I did. All right, negative 8.5, negative 2, negative 8.5 is here. Okay, so at r at negative 1, I'd get 2 times negative 1 plus 9 over negative 1. So that's going to give me negative 2 minus 9, which is negative 11. So that's not even on our grid. I guess it is. It's about here. So let's also be plotting our other stuff. We have negative 2, negative 17 halves on the graph. So positive 2, positive 8.5 will also be on the graph. And then positive 1, positive 11. So let's get one more. If we get r at, I don't know, how about negative 3, I guess? It would be 2 times negative 3 plus 9 divided by negative 3, so that's negative 6 plus negative 3, which is negative 9. So and then that means we'll have positive 3, positive 9 on the graph. So it looks to me like the graph is going to go something like this. All right, so let's see how we did by graphing it in the graphing calculator. So I'll graph the original version, which was 2 times x plus 9 divided by x. And look at that. We did it. Okay, so now let's go on to an application. So with this problem, we've got the concentration represented by C of a certain drug in a patient's bloodstream T minutes after injection is given by this equation here. So we need to find the horizontal asymptote and interpret what that means. So do you see this is a proper fraction. The degree of the numerator is less than the degree of the denominator. So therefore, the horizontal asymptote will be at y equals, good, 0. So what does that mean? As the time increases, the concentration approaches good, 0. All right. So now let's go ahead and graph this in our graphing calculator. So we have 50. We'll use x instead of t. And then we'll do the proper axes on when we write them in. And then divided by parentheses x squared plus 25. Now, is there negative time? No. So I'm thinking that if we just have a positive t, so we're going to set the minimum at 0, and then let's do the maximum at, this is t minutes, so let's maybe do the maximum. We'll try 30 minutes and see. Actually, I think that'll give us enough information. And then y minimum at 0. And y maximum, we'll just say 30. And let's graph it and see what that looks like. Oh, we don't need to go so high for the y value. So I'm going to go back to the y value and I'm going to go down to 10. Let's see what we got. There we go. So we need to figure out when the concentration is highest for our next item. So let's go ahead. I think this picture will be good for us. So this scale we had went from 0 to 10, and this is C, concentration at time t, and then the time we took to 30 minutes. So now they want us to figure out when the concentration is highest. So we would just look for the perfect, the maximum. So we go to the left of this hump here. And then to the right. And we get a maximum when x is 5, y is 5. So the concentration is highest highest 5 minutes after the injection. Is given. Okay? So you are all done for today. Have a fabulous evening, and I will talk to you soon. Bye.